Great, it's recording now. So let's talk about section 4.3, maxima and minima. Given a particular function, we are often interested in determining the largest and smallest value of the function, right? Let's say you are a CEO, you have access to the cost function for the production of items in your company. You may be interested in how low your cost could be, right? How or what is the minimum value for your cost function to keep everything running. On the other hand, if let's say you have access to the revenue function, another important question is how high you can go on your revenue, how or what is the maximum value of the revenue function, right? So maximizing, minimizing is something very important. So today, this is what we're gonna talk about, how to figure out the maximum value of a function, how to figure out the minimum value of a function, okay? And later on, we will use these techniques when we talk about optimization problems, right? To minimize or to maximize quantities using derivatives, right? Using derivatives. So it's gonna be useful. Gonja, welcome. How are you doing today? Everything okay? We just started.
Hi, I'm good, Professor. Sorry, I was late for homework.
It's okay. It's okay. It's okay. Don't worry. Yeah, we just started. We were basically saying that to figure out the maximum value of a function or the minimum value of a function is always important, right? Let's say you are dealing with a cost function. It's a natural thing to ask yourself, right? What's the minimum cost, right, for me to produce my items? And if you are dealing with the revenue function or even the profit function, right, it's a natural question to ask yourself how or what should be the highest value of my profit, the maximum value of my revenue, right? Yeah, things like that. So in this section, we will show how to find those absolute maximum, absolute minimum values of functions. Okay, so let's start with this example, right? Suppose you have a function and the graph of the function is this, okay? Now, let's try to identify what is the maximum value for the output values of this function. Clearly, if you walk through the function from left to right, clearly this is the highest value for the output values, right? So this is what mathematicians call absolute maximum, okay? Absolute maximum, right? The highest value, the largest value output wise, right? Now let's see how low we can go. The lowest output value. If I walk along this function from left to right, no hard to see that this is the lowest value for my output values, right? So this is what mathematicians call the absolute minimum, right? And then notice there are some values in between, such as this and this, that are maximum and minimum, but locally, right? Locally. In the neighborhood of this input value 6, for example, this is the highest output value, right? In the neighborhood of this input value 7, this is the lowest output value, right? So this is what mathematicians call local maximum, right? Because in this neighborhood, this is the maximum, and this one is called local minimum, because in this neighborhood, the neighborhood of 7 is the lowest, right? Now, also these 2 points are called in red here, right, where the function starts, where the function ends, are called endpoints. So let's write it here. 1 and 8 are called endpoints. So 1 and 8 endpoints. Well, endpoint. Okay, but now I want you to make this connection in your mind. Notice when we are dealing with this type of points, right, the top of these mountains, right, or the bottom or the floor of these valleys, right, derivative wise, what is happening? Well, remember in the last Desmos activities, we were looking at parabolas, and remember at the vertex, we figured out that the derivative is 0 always, right? So kind of the same thing is going to happen here, and I want you to make this connection from the start. Look, whenever you are dealing with either a maximum value for your outputs or a minimum value, derivative-wise, this is what's going to happen. The derivative there is going to be 0, 0, 0, 0, f prime 0. Why? Well, because notice the tangent line will be a horizontal line, right? Horizontal line. Similarly here, look at in this floor valley, right? For valley, look, the tangent line horizontal, so the derivative has to be 0 there. So derivative 0, intrinsic feature of these extreme values, right? Either max or min. Very good. Now, again, here, a local maximum, right? Derivative-wise, what's happening? Look, just like in the Desmos activity, right, at the vertex of the parabolas, right? The derivative 0 because the tangent line horizontal. So here, derivative will be 0. Welcome all you guys who just joined, Miguel, Ma. We just started. We're talking about maximum values, minimum value. Great, great. I'm doing great. Thank you for asking. Yeah, I hope you guys are doing well too. Let's just we're just basically saying that it's important to identify the maximum value and the minimum value functions. And for that, I'm going to give you some techniques. But the first thing I want all you guys to notice is that whenever these extreme values are achieved, look at what happens with the derivative. Derivative 0, right? Because the tangent line horizontal. Derivative 0 here also. Derivative 0 because the tangent line horizontal. Slope of tangent line that is horizontal 0, right? Here also derivative 0. Now, this is a special case. There is no derivative here, right? Because this is what mathematicians call a cusp. It's not smooth here. However, there is a local minimum. So derivative-wise, what can we say? Well, we can say that the derivative here is equal to dne, undefined, right? Undefined, because it's a cusp. Undefined. So to summarize, right? And I want you to again to make this connection in your mind. If you are dealing with the top of a mountain, a maximum, or the bottom of a valley, let's call it a floor valley, right? Then it is because the derivative is 0, or perhaps because the derivative doesn't exist. Okay, try to make that connection. That's the only way these extreme values can happen. Either if the derivative is 0, or perhaps if the derivative does not exist. Okay, yeah. Of course, we will go over this in details next. All right. So now mathematicians describe this point 1 and 8 as endpoints. We explained, right? But also, since these points are important, they are going to say mathematically the following. F, the function f, has an absolute maximum, right? The highest of all the output values here. 5, as you can see, right? The output value 5 at x equal 3. You see? At x equals 3, right? The actual maximum value is 5, but it happens, it occurs at x equal 3, right? So that's how they say it. Great. Similarly, for this point, f has an absolute minimum, right? The lowest of all the output values is this, of 1, right? Minimum value 1, and happens or occurs at x equal 5, right? Very good. Next, here, there is a top of a mountain, but it's not the highest top, right? This is the highest. However, this is also an important point. Later, we will look at this in details. It's called a local maximum because locally around the neighborhood of this input value 6 is the highest output value, right? Local maximum value of what? Of 3, you can see, right? And occurs or happens at 6, right? At 6. X equals 6. Great. F has a local minimum, this is special local minimum, right? Value of 2 at x equal 7, right? And it's due to this cusp, right? We said derivative doesn't exist, it could happen. Okay, great. Now, let's talk about some notation here. When mathematicians talk about absolute maximum or absolute minimum, they say absolute extremum. They call these points in general absolute maximum, absolute minimum, absolute extremum, okay? Now, similarly, when mathematicians are talking about a local maximum or a local minimum, right? Look, local maximum or local minimum, they just say local extremum, okay? Local extremum here. Now, maxima is the plural of maximum, right? Minima, plural of minimum. Also, local, the same as relative. So if you read our textbook and instead of local maximum, they say relative maximum, it means the same, right? Instead of local minimum, they could say relative minimum, right? All right, guys, great. So now let's talk about the extreme value theorem. What does it say, the extreme value theorem? It says that if you have a function that is continuous over an interval a comma b, all in one piece over an interval a comma b, right? Connected, right? No holes, no jumps. Then f achieves its absolute maximum and its absolute minimum on a comma b. So what the theorem says is that if your function is continuous, all in one piece, there is no way for the absolute maximum and the absolute minimum to escape. It will occur, that will happen within this interval, right? You can see, for example, if this is your function, here will be the absolute maximum, right? Absolute maximum. And if you continue here, absolute minimum, right? You will find them there for sure, if there is continuity. Now, it may happen once or sometimes it may happen twice. For example, in this other graph, the graph is continuous also over the interval a comma b, but turns out, look, the absolute maximum appears twice. Look here and also here, okay? Absolute maximum appears twice. And the absolute minimum appears just once. Absolute minimum, right? It could happen, right? More than once. Now, remember, continuous functions may not be smooth all the time, right? Sometimes the continuous function may come in this shape, right? Showing a cusp or a corner sometimes. It's a cusp, this one. But turns out this is now the absolute maximum, right? Absolute maximum. What the theorem says is that for sure you will be able to find the absolute maximum because there's no way for this absolute maximum to escape, right? Given the continuity, given that this is called connected. It will happen. And you may say, Professor, you found the absolute maximum. Where is the absolute minimum? Well, if you trace this, notice this endpoint turned out to be the absolute minimum, right? So sometimes the endpoints may themselves be absolute maximum, absolute minimum as well. But for sure, you will find both within the interval a comma b, right? This is what the theorem says. You may say, Professor, but this is kind of obvious. Yeah, because what happens is that mathematicians are formal thinkers, right? So they want always to state theorems in order to construct or to develop the algorithm, right? So continuity guarantees that you will find absolute maximum, absolute minimum within the interval. Great. So now, these points are special, right? The top of the mountains, the floor valleys, right? Mathematicians call them critical points. They have given a name to these points that are important. They call them critical points, okay? So the formal definition of a critical point is, let C be an interior point in the domain of F, right? say somewhere there. We say that C is a critical point, right, of f if the derivative is 0, right? The derivative is 0, like in here and here, right? Derivative 0. Or perhaps the derivative does not exist, like in here, right? Like in here, right? Derivative 0 or derivative that C is undefined, DNE, right? DNE. Does not exist. Example, on the graph that I showed you before, critical points are going to be 3, 5, 6, and 7. Why you say that, Professor? Well, look at this. Remember the definition of a critical point is either the derivative is 0, here derivative 0, right? Here derivative 0, another critical point. Here derivative 0, or perhaps the derivative doesn't exist, right? Doesn't exist. So 7 should be considered also as a critical point, right? So these critical points, 3, 5, 6, and 7. Now, there are some trivial critical points, the endpoints, 1 and 8, and in 99% of the text, they include them as critical points, so we will do the same. 1 and 8, I wrote a note here, should be considered also as critical points. I will show you here. 1 and 8, note, are also considered to be critical points since at those points, the derivative is undefined. Remember, for the derivative, you need variation, you need an open interval around the point. There is no open interval here, right? So it means that the derivative doesn't exist. So this should be considered also a critical point as well as this endpoint, right? Critical points. So we're going to include them as critical points. So you got to pay attention to all these guys, right? When you analyze your graphs, your functions, okay? Critical points. I'll show you now how to find those critical points. All right, so now we know what the critical points are. Here is a theorem due to the French mathematician Fermat. Here the Fermat's theorem, which is the following, which basically makes the connection between this absolute and local extremum and the derivative. It says, if f has a local extremum, it could be a local maximum, local minimum at C, and if f is differentiable, meaning smooth, then the derivative must be 0. So if you are dealing with a graph that is not only continuous, but it's also differentiable, smooth at some points, right? Then for sure the derivative must be 0. So if you have this graph, for example, here the derivative 0, right? At this point, derivative 0 here, derivative 0 here. This is what Fermat's theorem says, right? You may say, what do we do here, Professor? Well, here the derivative will not exist, right? Undefined. So here, derivative 0, derivative 0, derivative 0, here derivative undefined, DNE. So now these mathematicians write it as follows. F prime evaluated at 3, F prime evaluated at C equals 0. F prime evaluated at 5 equals 0. F prime evaluated at 6 equals 0. And F prime evaluated at 7, since it's undefined, you just write DNE, right? DNE. Very good. Okay, so now let's put all this stuff together and let's come up with a method, with an algorithm to find these critical points, right? Critical points. The algorithm the mathematicians figure out is this. Method to locate critical points of f of x. It comes in 3 steps. Step 1 says take derivative of f of x. You take the derivative of your function. Step 2, you're going to set the derivative equal to 0, and you're going to solve for x. That will give you the values of your critical points, right? But remember, this is not the only source to get critical points, right? Critical points also happen when the derivative doesn't exist, perhaps, right? So step 3 says identify, if possible, right? If possible, values at which the derivative is undefined, right? Undefined, DNE. So if you find values at which the derivative is undefined, then you have another source to get critical points. All right, example 1, find the critical points of this cubic polynomial function. Let me show you this, and then I will give you an exercise for you to work on. Let's follow the 3 steps, right? The 3 steps. Step 1 says, take derivative of your function, take derivative of your function. So we go ahead and take the derivative. So f prime of x should be equal to, notice, right? 3 comes down, 1 less stays here, 2, right? Minus 5 halves, constant, 2 comes down, 1 less stays here, 1. I don't have to write the 1, right? Plus derivative of 4x, just 4, right? Just 4. Now, derivative of our function should be, after canceling these 2, just x squared minus, after canceling this and this, 5x plus 4, right? This is the derivative of my function f of x. Now, step 2 says set your derivative equal to 0 and solve for x. We do that next. So we take derivative and now set the derivative equal to 0, prime equal to 0, and solve for x. So we're going to do this, right? X squared minus 5x plus 4 equal 0. And then we are going to solve for x. A question? Deep. Excellent. Yeah, Deep figure out the solution of this equation, right? We can use factorization, for example, or worst case scenario, we will have to use the quadratic formula, right? But there is always a way to solve a quadratic function. 2 numbers whose multiplication is 4, whose is negative 5 are, after some trial and error, 4 and 1, right? 4 and 1, but both must be negative. So 4 and minus 1 here, minus 4 here. Now, setting each factor containing the variable equal to 0, this leads to x equal 1, first critical point, and x equal 4, second critical point, okay? Second critical point, both critical points. Now, the step 3 says, this is not the only way to get critical points. Perhaps there are some input values that lead to derivative undefined. So I'm going to write here now, ask yourself, are there any input values such that derivative f prime of x equal does not exist or is undefined? Well, notice our derivative is super nice. It's a polynomial function, right? And remember, polynomial functions always exist. They don't have issues with undefined situations, right? So the answer for polynomial functions for your derivative is, for this question, is always no. Okay, no, because it's a polynomial function, the derivative always exists. So it means that we are done, because this is all we can get for critical points, 1 and 4, right? No critical points were gotten from derivative being equal to dne, right? So yes, 1 and 4. So conclusion, critical points are 1 and 4. Then 1 and 4 are the critical points. Points of f of x. That's it. Okay. Very good, guys. So now I want you to practice, okay? Before I go over more challenging forms, the first 2 are very easy. We could go ahead and do 3. Perhaps 3 should be good. Can you try to do number 3? Make it bigger. Find the critical points. The critical points of f of x. Okay. Yeah, so f of x, I'm gonna write it big here, x cubed minus 12x minus 5. Hint, follow the 3 steps, right? Set the derivative of the function equal to 0, right? Equal to 0. And solve for x, and solve for the summary of the 3 steps, right? Solve for x. And of course, then you have to check if for some reason the derivative may not exist, right? And then that's all it takes, right? So take the derivative, set it equal to 0, and get your critical points, okay? Go ahead. I see students readily posting answers. Deep, very good. Gonja, also good. Excellent, excellent. Yep. Yeah, you guys are sharp. You got it. You got it. Very good, very good. Yeah, very good, very good. Let's do it together, right? So we can see how this is done. Okay, so basically, in order to find the critical point, you have to find the derivative, right, of your function, which is this 3 coming down, x squared minus 12, right? 12. Now, next, out of convenience, I'm going to just factor, right? So that solving this should be easy. 3 out, 3 into 3x squared, minus minus, 3 into 12, 4. If I continue factoring this, since 4 is 2 squared, x squared minus 2 squared factors as x minus 2 times x plus 2, right? I got my full factorization. Then I just set my derivative equal to 0. And from there, I can get my critical points, right? Don't worry about this number 3, because if you divide both sides of the equation by 3, it will disappear. So don't worry about these constants, right? Just pay attention to the factors containing the variable, right? These are the important ones, right? This will lead to critical points. So x equal 2 is one of them, right? From here. And from here, x equal negative 2, right? So these are the critical points. Now you may say, Professor, you said we should check if we could get more critical points out of the derivative being undefined. But look at the derivative, guys. It's a polynomial function, right? Polynomial functions are defined for all real numbers. So there's no way for this to be undefined. So don't worry about that. No denominators, nothing. These are going to be only the 2 critical points, right? So this is it. Yeah. Great. Very good, very good. So moving on, perhaps you can try now this one, number 5. Let's see. Yeah, number 5 is a good one. Can you try this? Find the critical points. Again, hint, set the derivative equal to 0 and solve for x, right? Solve for x. This is what's going to give you your critical points when you deal with polynomial functions, right? Later, we will see cases where the derivative doesn't exist and you get some extra critical points from there. But for polynomial functions, guys, I'm telling you straight, derivative equals 0, solve for x is going to give you all your critical points. It's a little bit tricky. Yeah. Sometimes factoring might be tricky. So if you have another way to solve this, once you take the derivative, follow it, you should be fine. As long as you get your critical points, you should be good to go, right? I see some activity in the chat. Gonja, yeah, you made my day. Gonja, excellent, excellent. Very good, very good. Yeah, you got it, you got it. Very good, very good. Yeah, so let's do it together, okay, to explain. So here, again, I have a polynomial function, 3 steps. First step says take the derivative, right? Derivative of the polynomial function. The derivative is going to be 3 coming down, multiplying 20 is going to be 60 x squared minus 5 coming down, multiplying 3 is 15 x to the 4 power, right? Now I am going to factor so that I can easily solve this. First, I noticed that 60 and 15, they have greatest common divisor 15, right? X squared and x to the 4, I picked the one with the smallest exponent, x squared, greatest common factor, right? What mathematicians call GCF. If this is factored out, what is left inside? 15x squared into 60x squared is just 4. Minus, 15x squared into 15x to the 4, 15 into 15, 1x squared into x to the 4, x squared. This is left, right? Yeah, now, carefully. I'm going to continue the factorization, okay? F prime of x equal 15 x to the second power. Notice this guy is 2 squared. 2 squared minus x squared. Using difference of the square, 2 minus x times 2 plus x, right? That's it. Now I set this guy equal to 0 and solve for x, right? Solve for x. So 15 x squared times 2 minus x times 2 plus x equals 0. 15 is a constant. I said, don't worry about this constant, right? Because if you divide both sides by 15, it will be gone. It's disappeared, right? This is still 0. So pay attention to this guy, right? X squared equals 0. 2 minus x equals 0, right? The factors contained in the variable, set them equal to 0, right? From here, taking square roots in both sides, the square root of 0 is 0, first critical point, x equals 0. From here, transpose x to the other side, x equal 2, right? Another critical point. Here, minus 2, x equal negative 2, another critical point. So the critical points are 0, 2, and minus 2, right? 0, 2, and minus 2. Excellent, excellent. This guy, right? In any order, it can be presented.
Professor?
Yeah, question. Go ahead.
It's Ma. So you decided to do 15 over 15. What I did was, during my calculation, I did 15x squared on both sides. I divided both those. So that's wrong. We can't do that, is what you're telling me?
Let's back up a little bit, okay? Yeah, you said, Gonja, that you got this, right? 15x squared, 2 minus x, 2 plus x equals 0, and then you divide it by 15x squared, both sides?
Yeah, and then I got rid of it.
Yeah, there is an issue there, Ma, because look, I know that 15 is not 0, right? I know, right? Yes, that's why I feel free to do this. But the issue with including this part is that I do not know what x is, right? X could be 0, and if x is 0, we're in trouble there. So for these divisions on both sides, you have to do it whenever you are sure that this guy is not 0. That's why only 15, right? You follow?
Oh,
yeah.
Okay.
X squared
And should
has
I do
to
that
stay.
always?
Yeah,
Whenever
always.
I'm doing a calculation. Okay.
Always. When you solve equations, never divide both sides by x, not knowing that x is 0. If you know that x is not 0, you can do that. But here we don't know. And actually, one of the solutions is 0, right? So you see?
Right. Yeah.
The problem is if you do this, you're gonna miss this guy. You're gonna miss this 0, right? Yeah, very good. Good question, Emma. Yeah,
Thank
great.
you.
Yeah, let's write this as a note, right? Note. Yeah, very good. Okay, great, guys. So moving on. Now we have these forms, right? Look, this composition of functions. So let me give you one more example, and we will go back to this, okay? So let's go back to the lecture, and let's see one more example here. Here. Yeah, we did this. Yeah, then this is done. Let's talk about this one now. Example 2. What if they give you something like this? Find the critical points of this function, f of x equal x squared minus 1 cubed. Okay, let's do that together. If they give you something like this, follow the method. The method says take derivatives, right? Take the derivative of your function, whatever it is. It's a composite function, not a problem. We have the chain rule to deal with these composite functions. I'm gonna use here f of x equal this function. I'm gonna rewrite it as this cube function, outside function, and x squared minus 1 inside function in red. So the derivative of this composite function should be derivative of the outside function 3 is square. What is square? The x squared minus 1, right? The inside function stays here for a moment, and then times what comes here. Anyone could tell me what's the derivative of x squared minus 1?
2x.
2x. Excellent, excellent. 2x, right? 2x, derivative of the inside function. Excellent. This is the derivative, right? And it actually came out well because it came out in factor form, right? And we need that next because now you simply simplify this a little bit, right? 3 times 2 is 6. Let's write 6x up front. Remember, follow what mathematicians do, right? The simple stuff up front, the complicated stuff following at the end. So this is my derivative in nice factor form, right? Yeah, very good. Now the next step is set the derivative f prime of x equal to 0 and solve for x, right? Solve for x. This is what we're gonna do next. So 6x times x squared minus 1 squared equals 0. I have a chance to factor this also. Look, x squared, notice x squared minus 1. 1 is the same as 1 squared, right? The same. So I can use difference of squares there. But carefully, look, this is going to be x minus 1 times x minus x plus 1, right? This, but it's a square. So the square gets distributed. We end up with this, right? You follow that? Again, this part is this. Maybe I have highlighted. So now I get confused. This part was this, right? But since it's a square, they have to be both square, equal to 0. Bottom line, this number 6 shouldn't bother us because dividing by 6 both sides, we know it's not 0, right? We get rid of it, right? Let's do it nicely. We end up with this. Look. X times x minus 1 squared times x plus 1 squared, all equal to 0. Full factorization. From there, just set equal to 0 each, right? And that's it. X equals 0, one critical point from here. X minus 1 squared equals 0. Taking square roots, x minus 1 equals 0, x equal 1. Second critical point. Similarly here, x plus 1 squared equals 0.
Negative.
Taking negative 1. Excellent, excellent. Thank you. Taking square roots, both sides, 0. And finally, negative 1, right? Moving or transposing 1 to the right side. 0, 1, and negative 1 are going to be our critical points. So conclusion here. Critical points are these 3, right? You may present it in any order: 0, 1, and negative 1. Okay. All right, guys. So this is what you should do if you see composite functions, right? Composite functions. Sometimes students say, what if I just take this, make it equal to 0? You can do that too, guys. You take square roots, and as long as you catch these two, 1 and minus 1, right? It's fine. So now, try to do something similar here. This one, for example, I think is good. Number 7 or 6. Yeah, this one should be good. Can you try this guy? Number 8. Numbers more interesting 6, I think, because 6 or 7, I think is good. Yeah, 7 is good, I think. It's a fifth power. Yeah, try to find the critical points of this function. Find the critical points. The function is f of x equal x minus 10 raised to the 5th power. Can you do that? Yeah. Take derivative, hint hint set derivative of the function equal to 0 using the chain rule, right? And solve for x. Solve for x. Yeah, and at this point, since we're dealing with polynomial function, we are not paying attention to where the derivative doesn't exist, right? Later we will do that. But for now, as I explained, right, since the derivative comes out to be a polynomial function, that's the only source for us to get the critical point. Mhm.
Professor,
Yeah, go ahead, Kunju.
can it be only one answer? I mean, one
One
number?
critical point.
Yes.
Could be, but in this case, you're
Not?
gonna be careful. No, you're talking about this question. Yeah, this question
Yes.
turns out, yes.
Yeah,
That's definitely,
I
yeah, you
found
got it.
one number, which is
Yeah.
B.
Yeah, excellent.
But I wasn't
think you got
sure
it.
if you can find one number. So it-
Excellent. Yeah, you got it.
Okay.
Because it's the answer. Yeah, excellent.
Okay,
Yeah,
thank you.
yeah. In mathematics, sometimes the results are surprising, but if you follow all the steps, all the rules, right, and you should be fine. Yeah, this is the right answer. Very good. Yeah. And
Professor,
actually, let's do it together. Yes, go ahead.
sorry, would this be like our maximum or our minimum at this point? Like,
At this point,
because we only have one answer, so.
yeah, at this point, we are sort of finding the candidates that are going to lead to maximum or minimum, absolute maximum or absolute minimum. We are not in the next part, in the second part of this lecture, I will show you how to identify this with either a maximum or a minimum. But right now, we are just finding the candidate, right? The special input values. All right, let's do it together, guys. So we're gonna take the derivative, right? And since this is a composite function, it would be a good idea to identify clearly the outside function as the fifth power function and the inside function as this function, right? X minus 10. When you take the derivative using the chain rule, phi comes down here for one less x minus 10 inside function here. And who can tell me what's the derivative of x minus 10? Derivative of the inside 1, right? Excellent. 1, right? So 1, which is not going to change this, right? So bottom line, this is going to be just this, the derivative 5 times x minus 10 raised to the 4th power. Great. Now, next step says set your derivative, right, equal to 0 and solve for x, right? And solve for x. When you set your derivative equal to 0, first get rid of this 5, right? Dividing both sides by 5, right? The 5 disappears. This is still 0, right? So we end up with x minus 10 raised to the 4th power equal to 0. Take 4 root in both sides, and the 4 root of 0 is plus minus 0, but plus minus 0 is a 0, right? So we end up with x minus 10 equal to 0. Adding 10 to both sides, very good. X equal 10, right? Just one critical point, which happens to be this, right? It could be, sometimes there are 2, sometimes there are 3, sometimes there is 1, sometimes none. Okay, yeah, try to remember this on your homework. Now, I don't look for values of x such that the derivative doesn't exist, because this derivative is a polynomial function. Polynomial functions are defined for any value of x, right? So that's it. Very good. Okay, now let's see the case when we actually have to look at values of x such that the derivative may not exist, it could be undefined. Let me show you an example first, then we will go back to this. Hint, it appears when you see square roots or when you see denominators made out of the variable, right? So in those cases, you have to be careful. I will show you with an example how you proceed. But before we do that, yeah, let's see. I don't have an example here. I can show you directly then on the worksheet. Maybe I can show you this, number 9, and then you can do 10. Okay. Yeah, let me go ahead and do number 9. Suppose they ask you to find the critical points on this function, right? Y equal to x squared minus 64 square root of x. Okay, so let's say you take the derivative of this part to x squared is going to be just 4x, right? 4x. Derivative of this part, 64 constant comes out. What is the derivative of a square root of x? Well, recall the derivative with respect to x of this nice function square root of x is in simplified form this 1 over twice square root of x, right? So that will come next. 1 over twice square root of x. Derivative of this part, right? Now, this is the derivative, right? The derivative is showing us now denominators, right? So this is sort of a sign that we have to be careful here. Okay, great, right? 2 into 64, 32. Now, we are supposed to set this equal to 0. Set your derivative. Yes, go ahead.
Why we didn't, this is Ronja. Yeah, why, why we didn't put the 2 square root of x?
Because this 2 into 64 is just
that's right.
32. Yeah, that's okay. Right. But good remark. Yeah, excellent. Right? Yeah, the 2 goes into 64, 32. Great, excellent. All right, great. So now setting this guy equal to 0 and solving for x, what's going to happen? Look, it's going to happen the following. This, I'm going to move or transpose this term to the other side. I'm going to get this, okay? Very good, right? I just added this amount to both sides, I get this, right? Now, at this point, one thing I can do to get rid of this square root on the denominator, I can multiply both sides of this equation precisely by that square root, right? Square root of x here times square root of x here. So I am going to get 4x square root of x here. And over here, these two will cancel, right? So 32. Little by little, look, the equation gets smaller and smaller. Now, perhaps I can divide both sides by 4. That would be a good idea, right? To eliminate this guy from here. And I end up with this. 4 into 32, 8, right? 8. Now, what is this guy? Isn't square root of x just x raised to 1/2, right? 1/2. And isn't it x equal to x raised to 1, right? True, right? So now, multiplying these two guys, I keep the base and I add 1 plus 1/2. Over here, 8. But 1 plus 1/2, once you do it using the LCD and all that, is 1 is the same as 1 over 1. LCD is 2. So if you multiply this by 2, this by 2, you will get 2 plus 1, 3 halves, right? 1 plus 1/2, 3 halves, right? 3 halves equal 8, very close to the end, okay? Now, I want to isolate x, right? I want to get x by itself. So what we're gonna do next is we're gonna raise these two sides of the equation to this special power, the reciprocal of this. This is 3 halves, so I have to use 2/3 here. Raised to 2/3. Look, 3 cancels with 3, 2 cancels with 2. This gives me x all by itself, look, as I need it, right? And that equal 8 raised to 2/3. Now, this 8 raised to 2/3 can be found in the calculator, right? You don't have to do it by hand, but if you want to do it by hand, this is just cube root of 8 squared, right? The denominator is the index, this is the exponent. 8 squared is 64, and cube root of 64 is just 4. But all this can be avoided if you just go to your Desmos Scientific Calculator and put this a raised to parentheses 2/3, right? What do you get? 4, right? What I got there using all these tricks. Yeah, 4. This is what is important, guys. Don't get stuck. Use your tools in case you need them, right? X equal 4. After all this, I got one critical point. Look, x equal 4. But now the question for you guys is this. Is this going to be my only critical point? Shall I just pick D there? Or is there any other source from where I could pick up more critical points? It's a tricky question, right? Because before we just solved the equation and we got for that our critical points. That is because we were working with polynomial functions, right? They are very nice. The derivative was always defined. But here, if you pay attention to the derivative, to the form of the derivative, could you tell me, anyone could tell me for what value of x this derivative is undefined?
0.
0. Excellent, excellent, excellent. Right? So basically, you ask yourself, right? Are there any value or values of x such that y prime equal does not exist or undefined? And the answer in this case, yes, yes. For x equal, thank you, 0, right? 0. Look, if you put 0 there, you're going to be in trouble. Square root of 0, 0. 0 into 32, undefined. You're going to be in trouble, right? So this means that this x equals 0 is also a critical point. So conclusion, critical points, 0 and 4, both, right? Not just 4, 0 and 4. So you gotta go this 0 and 4, right? You follow, guys? That was for question number 9. Yeah, very good, very good. All right, this theorem says the following: let f be a continuous function over an interval a comma b, then the absolute maximum and the absolute minimum occur either at endpoints a or b, right? Probably here or here, or perhaps at critical points of f. And remember, the critical points of f are the ones where the derivative is 0 or where the derivative doesn't exist, right? So this theorem basically is giving us a way to kind of look for this absolute maximum, absolute minimum, right? It says that if the function is continuous, there's no way for the maximum and for the minimum value of the function to escape, right? It has to happen within the interval, or perhaps worst case scenario at this endpoint, right? Notice, for example, if you are dealing with this function, here, we have critical points, right, where the derivative is 0. But also, perhaps the derivative may not exist. Let's make it more interesting here. Let's create a little corner here, or a little cusp. There we go, right? So what this theorem is saying is that you should look at these places, endpoints, or perhaps where the derivative is equal to 0, right? Look, if I look through, turns out here I can find my absolute minimum, right? Happens when the derivative is 0 here at the floor value here. And the absolute maximum happens here. Absolute maximum, right? So this kind of help mathematicians to come up with this method to find absolute extrema. First steps, they say, find all critical points, right? The input values that lead to derivative 0, or the ones that lead to derivative undefined, right? This, and this. Then evaluate f, the function, at the endpoints, right? Let's say here and here. And at the critical points, right? And compare them, right? It says comparing the output values, get some absolute maximum and absolute minimum, right? So we find the critical points, and together with the endpoints, we do evaluations. And then according to the table of the results of those evaluations, we will get our absolute maximum, our absolute minimum, right? Yeah, it's just a simple method. Let me explain to you how this method works. Example 1 says, find the absolute maximum and the absolute minimum of this cubic function x cubed minus 12x plus 5 over this interval, minus 3, 5, over this closed interval. So let's see how this works, right? Yeah, here, let's just write here derivative 0, derivative 0, and here derivative undefined, does not exist. There is going to be an applet on your homework where they're going to ask you to identify the critical points. Always go to the top of the mountain, floor valley, right? And where the derivative doesn't exist, where you find these cusp corners, right? Go there. All right, so let me explain to you how this works, right? In step 1, we are supposed to find our critical point, right? But we know how to do that. All it takes is find the derivative first. Derivative here is 3x squared minus 12. Derivative of the 0, right? And then we are supposed to set our derivative equal to 0, right? To find our critical points. Now, if you set this equal to 0, several ways to solve this equation. Follow whatever you feel comfortable with. I'm going to factor 3 out. If I factor 3 out, 3 into 3x squared, x squared, minus 3 into 12, 4, right? And at this point, I can just set this equal to 0, but let's say I continue factoring and I get this full factorization, right? Remember, this guy is 2 squared. Difference of a square leads to this. Then remember, we don't care about these constants outside because they disappear as soon as you divide both sides by the constant, right? You end up with this. And then this is telling us that our critical points should be x equal 2 and x equal -2, right? These are our critical points. But now we're going to go a step further. Now, we are going to do evaluations, right? Recall our function, the one that we are dealing with in this exercise. You don't see this up there. What's this? X cubed minus 12x plus 5, right? Plus 5. This was our original function. What it comes next is evaluations, x here, f of x here. At what points? Well, start with the endpoints. Start with the endpoints. This guy and this guy. Start with the endpoints, okay? So this is gonna play the role of your A. This is gonna play the role of your B, right? Endpoints. So start with that. -3 and 5. So on the table, you start with -3 and 5. And you leave some space to write in between your critical points. 2 and -2, right? So when I put them in between. So -2 here and 2 here, okay? So we're gonna evaluate at all these special points and the outputs will come out. We will compare the outputs and from there we will pick up our absolute maximum and our absolute minimum. Okay, so let's start doing the evaluation. Let's take the calculator, our decimal scientific calculator. Let's start with the first evaluation. The first evaluation is saying, okay, evaluation of -3. What's that? So parenthesis -3 cube minus 12 times -3 parenthesis plus 5. I got 14, right? 14. Great. I'm gonna hit enter and next I'm going to copy and paste this here. And I'm gonna just change the inside part for -2 now. -2 here.
It's 21.
21. Excellent, Concha. Great. Now, again, paste and change it for 2, the critical point, right?
-11.
-11. Yep. Very good, guys. Work efficiently, right? Great. And finally, I have to evaluate a 5, right? So one more time.
70.
Say, excellent. 5 here, 5 here, 5 here, 70, right? You see all the output values, right? So this is what goes here, what you have to write here, and then we will just compare them, right? We will just compare them. From there, we will pick up our absolute maximum, absolute minimum. So I am going to write 14, 21, minus 11, and 70, right? Yeah, very good. Let's do that. So the first evaluation gave us 14, second 11, third, no, the second 21, third negative 11, and the last one gave us 70, right? So comparing the overall, clearly this one is right here, conclusion. This one is the absolute minimum, right? Minimum, absolute minimum. And clearly this one is the absolute maximum, right? And that's all we were able to find, right? Okay, guys, so can you try now one on your own? Let's go to the worksheet and let's start with these polynomial functions first, and then I will show you some special cases. All right, so you compute the critical points, then you evaluate them, right, together with the endpoints, and that should give you the answer. Let's do one with a polynomial function first. These quadratics are kind of easy. Let's pick a cubic one. Number 3, I think is a good one. Can you try this? I will give you time to try this one. Figure out what are the maximum value and the minimum value, right? And together with the critical points. And remember, the endpoints are also considered critical points, right? Remember, we explained that. And the hint is start by taking the derivative, setting it that equal to 0, right? Yeah, hint set the derivative equal to 0 and solve for x, right? It starts with that, solve for x. That gives you the critical point, and then you come up with that nice table, right, that I show you. And then from there, you get all your, well, you get the absolute minimum and the absolute maximum, right? Yeah, let's write the function big here so everybody can see f of x cubed minus 12x plus 1, right? Start by taking the derivative. Yeah, and then I will show you what to do when they give you these fractional exponents, right? It's a little bit trickier there.
Is it D? D.
Close, Gonja. D as in David?
Yes.
Very close, but I
then
think
no maximum value.
No, there is maximum and there is minimum. Yeah, both. And remember also you have to put together the once for the critical points, the endpoints, these two guys should go there. This and this as critical points, right? We explained that, right? Because formally speaking, the derivative doesn't exist there. So it could be the first one or maybe this, one of these two, right? Critical points, the endpoint. Mhm. Mhm.
Okay.
Okay. Any guess? Any educated guess?
Yes,
I don't know. I think I found.
Yeah. Go ahead. Go ahead. Yeah.
Did I find A? I think I found no. Yeah.
I don't know. I'm getting my critical point
No,
as
it's
under
C,
root
C.
6.
Uh-huh.
It's C.
Yeah. 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 Who said C? I think was it Gonja?
Gonja.
Yeah, excellent. Gonja, you made my day. Yeah, it's C. It's C. Yeah, it's a little bit tricky. It takes a lot of steps, but indeed it's C. Yeah, very good, very good. Great. Okay, let's do it together. Okay, so we can go over the special cases when when they give you some functions with fractional exponents. So it all starts by taking the derivative, because the derivative will give us access to the critical numbers, right? So 3x squared minus 12. Derivative of this 0. Now I'm going to factor my derivative, because next I have to set my derivative equal to 0 and solve for x, right? Solve for x. So factoring my derivative, I get this. 3 is the greatest common factor of 3x squared and 12, so 3 out. 3 into 3x squared, x squared, minus, 3 into 12, 4, right? Then I continue the factorization here. This 4 is 2 squared, remember? So this is going to be x minus 2 times x plus 2, right? Full factorization for my derivative. Now, when you set this equal to 0, you're going to get the following, right? Dividing by 3 both sides, I get rid of the number 3 here. X minus 2 times x plus 2 equals 0 leads to x equal 2 for the first critical point, and x plus 2 equals 0 leads to x equal negative 2 for the second critical point, right? These are the critical points. Now, what is next? We have to create this table, right? Remember the table? The table x, f of x, conclusion. Here we're going to write the endpoint first, right? This guy, maybe I should do this. These two, they go always here, negative 3 and 5, right? Negative 3 and 5. In between, if these guys are in between, you put them there, right? 2, negative, and 2. Let's do it in order. And now evaluations, right? Evaluations. So you take the original function. I'm going to do evaluation on all these guys. So you take your calculator. I'm going to use our Desmos Scientific Calculator. And I start with the first evaluation. The function is x cubed, so negative 3 cubed, minus 12 times negative 3, plus 1, right? Plus 1. The first evaluation gives me 10. Gives me 10 for the first evaluation, okay? Now for the second evaluation, I'm gonna just copy and paste this here. And instead of negative 3, now I'm going to evaluate the first critical point, negative 2. Negative 2 here, negative 2 here. The rest stays the same because I'm still evaluating at this function, right? The original function. I got for the second evaluation 17. I continue this process, copy and paste this here. I am going to evaluate at the number 2 now. So write this 2 here, erase negative 3, write instead 2. The value that I get is minus 15, right? Minus 15 for this guy. And finally, the last evaluation should be at 5. So paste here and then replace this for a 5. 5 cubed minus 12 times 5 plus 1. That is equal to 66, right? So I'm gonna write the evaluations here, right? And then we will make a decision, right? Evaluations, and we will make a decision. So let's do that. So the evaluations were 10 for this guy. Then I got 17 for this guy. When I evaluated at 2, I got minus 15. When we evaluated at 5, we got 66, right? Look at the overall. Look at this. This is the smallest output value. So this has to be the absolute minimum, right? Minimum. Look at this guy. In the overall is the absolute maximum value for the output values, right? Absolute max, right? Yeah. Very good. So then the answer should be this, including the endpoints, are the critical points, right? This, and this is absolute minimum, absolute maximum. So you gotta go with this guy, right? See, follow, guys? Yeah, tricky, very tricky. So be careful, okay? That's how you do it. All right, guys. So now something that you should know. The reason I included this guy here and this guy here, yeah, sorry, this is because they are in between, right? They are in between. If for some reason your critical points are not between the interval, or just one of them is between the interval, so you just include that ones, the ones that are in between, right? These two were between -3 and 5, right? They were inside. But let's say you get a critical point 7. You don't have to use it because they are asking you to get the maximum value here within this interval, right? You follow, guys? It has to be inside for you to include it in the computation on the table. Okay, now let's see some special cases. Look, these kind of things, right? Don't get freaked out when you see functions like this. You just have to be careful. I will explain. Or this, right? Exponents that look like fractions. How you go over those. Let me show you the next example. It's here, I think. Yeah, here. This nice example that's going to help you also with your homework. Example 2 says, find the absolute maximum and absolute minimum of this function x squared minus 3 times x raised to 2/3 fractions, right? Fractional exponent over this interval from 0 to 2, from 0 to 2. Let's do it. All right, so step 1, we are supposed to find the derivative, right? The derivative is always the first step because it will take us to our critical points. So derivative first, derivative. So f prime, what should be f prime of x? Derivative of x squared is twice x, right? Right. But what's the derivative of this guy? 3 times what? The exponent comes down as 2/3, right? And what it stays? 2/3 minus 1, right? Minus 1. Let's do it carefully. Now, this should be equal to what? Twice x. 3 and 3, they cancel. Minus 2x raised to what? What is 2/3? Negative 1/3. Thank you, right? Yeah, in case you don't see it, that the negative 1/3, it just comes from here, right? This is 1, LCD 3, so you multiply this by 3, this by 3. And here on the bottom, you have 3, common denominator 3. On the top, you have 2 minus 3 minus 1, right? Minus 1. So this is minus 1/3. Very good. Excellent. But now we are supposed to set this equal to 0. So in order to do that, allow me to rewrite this, right? Rewrite this polynomial derivative as this: 2x minus 2 on the top, this x raised to 1/3 on the bottom. But x raised to 1/3, isn't it just cube root of x, right? So this should be what the derivative is, right? In a nice form. Okay, now we are supposed to, someone wrote something in the chat. Gonja, yeah, excellent, excellent, right? Yeah, it's some algebraic work there. Yeah, I see you following. Great, this is what we get, right? Now, next, we're supposed to set this equal to 0, right? Set f prime of x equal to 0 and solve for x, right? Solve for x to get our critical points. If you do that, if you set this equal to 0, then you have to do twice x minus 2 cube root of x equals 0, right? I'm going to transpose this to the other side. I will get this, right? Change the sign, right? It's like adding this to both sides, right? This disappears here, this guy appears here. And next, what we can do? Well, I want to get rid of this denominator. Allow me to multiply both sides of this equation by cube root of x, right? Precisely this denominator that is bothering me there. All right, let's get rid of this. You're gonna get 2 equal here 2x cube root of x. Now, what is that? And by the way, if 2 is bothering you there, you can get rid of it dividing both sides of your equation by 2, right? A lot of mathematics professors, yeah, it's just the nature of these problems when you deal with fractional exponents, right? You will end up with this. What is this? Isn't it just x times x raised to 1 times x raised to 1/3, right? Cube root of x is the same as x raised to 1/3, right? That's equal to 1. This, in algebra, you learn that this is 1 plus 1/3, right? So again, we have to add this to fractions. Here, 1 below, LCD 3. 3 times 1, 3, 3 times 1, 3, 3 plus 1, 4. 4/3 is what I'm gonna get here, right? 3 common denominator, 4/3. Great. But now, finally, I can raise both sides of this equation to this special power, the reciprocal of this. What you get when you flip this, right? 3/4. 3/4. If you raise both sides of this equation to 3/4, notice this guy is going to cancel this, giving you x by itself here, right? By itself, completely by itself. And what is, who can tell me what is 1 raised to 3/4? 1 raised to 3/4? Remember, 1 is special when raised to different powers.
Is it 1?
1. Excellent, excellent, excellent. 1, right? Good. 1 raised to any power is 1. Great. So finally, Professor, after struggling, we got our critical point, x equal 1. Are we done? Unfortunately, guys, this type of function has led us to a special type of derivative, right? Look at this structure of the derivative. So this is a critical point, x equal 1, right? But now you got to ask yourself, remember, is there another value of x such that the derivative does not exist? When you look at this derivative, anyone could tell me for which value of x this derivative is going to be undefined?
0?
0, right? Yeah. Yeah, so we're going to write here also for x equals 0, f prime of x equal undefined, right? Fine. So you got to add this as your critical point. So x equals 0 and x equal 1 are critical points, right? 2 critical points, not just 1. So now, time to go to the table, right? Time to go to the table. I got 2 critical points, right? 2 critical points. So remember, for a table, you write x here, f of x here, and here your conclusion. Your conclusion. Start by considering the endpoints, right? The endpoints. And what were the endpoints? Well, these guys, right? I'm gonna highlight them so that you will remember. 0 and 2 are the endpoints, right? 0 and 2. So the table starts with the endpoints, 0 and 2. Leave some space in between for the critical points, right? 0 and 1. Leave some space in between. Okay, and now be careful here. we said 0 and 2 were the endpoints, right? And we can probably highlight them so you will remember. 0 and 2. Yeah, great. Now, in between, we write the critical points, but be careful there. Be careful, make sure that they belong there. For example, 1 is it between 0 and 2? Yes, right? It's there. 0 is also between 0 and 2, but it's already there, right? So only 1 should be included, right? You agree, guys? Only 1, because 0 is already there, right? So now we're going to do the evaluations. At 0, what should be f of x? Remember f of x, I'm going to rewrite here f of x. It was, recall, it's up there, right? Is x squared minus 3 times x raised to 2/3 in its original form, right? So if you evaluate x, f of x at 0, 0 squared 0, 0 raised to 2/3 0, 3 times 0, 0, I'm going to end up with 0, right? Yeah. And again, guys, if you don't have to do this in your mind, you can just use the calculator. Right? See, this 0 is squared, sort of to follow the format that we were following for the other exercises. The first evaluation is this, right? Raised to 2/3. The exponent is a fraction, but we're okay with that. Yeah, 2/3. Great. So this was 0, right? First evaluation. Second evaluation at 1. At 1 is also easy because this will be just 1. And this, I gotta copy and paste this new one. At 1 now, right? I think it's gonna be just -2. 1 is squared minus 3 times 1 raised to 2/3 is 1, 3, 1 minus 3, -2, right? See? That's the second evaluation. The last evaluation should be at 2. The original equation, right? Original function, there's it. Original function, you do the evaluations. When you evaluate at 2, you get this decimal, right? 2 squared minus 3 times 2 raised to 2/3 minus 0.762 approximately, right? So let's write it out. So let's write out our result. 0 minus 2 and minus 0.762. Let's write it out here, okay? So 0 minus 2 minus 0.762, right? Now look at on the overall, right? In the overall, what is the highest? What is the highest value? Anybody could tell us what is the highest value for a conclusion?
0.
0. Excellent. Excellent. This
0.
one, maximum, absolute maximum, right? Yeah, let's write it. And the minimum value, what should be the minimum value?
-2.
Negative.
-2, right? Because this is on the left of -0.762, right? When you put it on the number line, excellent, excellent. So this will be absolute mean, right? And then basically we are done because this is absolute maximum, this is absolute minimum, right? We found them, but it took some work because of the inclusion of these critical points coming out of the derivative being undefined, right? Just because the function was special. All right, guys. So now I want you to try this technique with,
Professor?
Yeah, go ahead.
I'm sorry, just a
Question.
question. So is -0.76 our like local minimum?
Yeah. Yeah, thank you. Yeah, very good. Look, here we are not identifying yet the local maximum, local minimum, right? But in 2 lectures from now, then we will. This will qualify for either local minimum or local maximum, perhaps. They call them local extremum. Yeah, it will. Okay. But right now, our goal is just to catch the highest and the lowest, right? The highest and the lowest. That's it for this lecture, right? Later, we will see this. This is a special values too. Excellent. Yeah. So now I want you to try this one. Give it a shot here. I have a couple here. Yeah, let's start with this. With the exponent. Let's just demystify it, right? Can you try this? G of t is this function, t raised to 2/3. And they say, find the absolute maximum and the absolute minimum over this interval, -1, 8, right? As usual, the hint is set the derivative of this function equal to 0 and solve for t, right? To find the critical points first, and then you construct that table where you're going to put together this and this, first this, last this, and in between the critical points, right? And then following that table, you should be able to identify the absolute maximum, the absolute minimum, right? Yeah, so try guys. And if you have questions, as usual, just let me know. Very tricky, this problem.
It is. I can't find
Yeah.
the
Yeah, it's okay. We can try it together. Yeah, Konja, very close, Konja, but remember, yeah, there is a trick here. Yeah, let's do it together for me to show you the trick, okay? We start with a function, right? And then we have to take its derivative, right? Because the derivative is going to give us the critical points, right? So let's take the derivative. The derivative is going to be 2/3 comes up, right, up front, t raised to 2/3 minus 1. Again, these fractions will appear, but that shouldn't be a problem because this is 1, LCD 3, so times 3 times 3. We know that this guy will end up being just this. 2/3 t raised to 3 is the common denominator, 2 minus 3 minus 1, right? This guy. Now, this guy written nicely, right? First, to make it positive, let's put it down, t raised to 1/3. And second, remember mathematicians prefer radical form over fractional form, so this should be just cube root of t, right? Yeah, this that. Yeah, it's a special function. Now, we are supposed to set this guy equal to 0. But look what's going to happen when we do that. 2, 3 cube root of t equals 0. If I multiply both sides of this equation by cube root of t,
we lose our t.
Yeah, we lose our, yeah, this will cancel this, right? 2/3 equals 0, right? But this kind of things, mathematicians call it a contradiction, right? A contradiction. This is a contradiction, can never be. The number 2 divided by no number is going to give you 0. This is what this is saying. So when you reach a contradiction in mathematics, what do you conclude? Then you say no solution from here, from this source, no solution, okay? But remember, guys, this is not the only source to find critical point. There is another source, right? There is another source that say, look at the structure of the derivative and try to figure out for which values of t this derivative may be undefined. Can anyone tell me for which value? Aha, excellent, right? Notice for x, or t to be formal, right? For t equals 0, g prime of t does not exist, right? From t dne, undefined, right? Undefined. So this means that then 0 is a critical point, right? Critical point. So we were not able to extract a critical point by setting the derivative equal to 0 because we ended up with a contradiction, but we were able to extract a critical point from the second condition, right? By picking up input values that make our derivative undefined. So 0 is a critical point. So then it means that we can include that in our table, right? In our table. So let's go to a table. And remember on the table, you start with t, then you go ahead with the function g of t, and then conclusion. And here you start with the endpoints, right? What were the endpoints? Well, the endpoints are -1 and 8, right? -1 and 8. So these are the endpoints. So let's start there. -1 and 8. And in between, we are supposed to put the critical points. I'm going to highlight this so you can make the connection later if you're looking at the notes. These are from endpoints, but in between, we got this critical point, right? 0. And it's true that 0 is between -1 and 8. So we have to put it there, right? Great. Now let's go ahead and do evaluations on the original function. Recall the original function g of t was this function. T raised to 2/3. This was the original function. So there we have to do the evaluation. So first evaluation should be this -1. This, you can use the calculator, right? So -1 raised to 2/3, right? 2/3. 2/3. I get 1, right? Because it's the cube root of this square, 1. Yeah, 1 will go there. At 0, clearly this will be just 0, right? 0. So let me just copy this and paste it here so I can see. At 0 is any exponent above 0 except for 0 gives us 0, right? Great. So now, finally, at 8, this guy evaluated at 8. I'm just changing the input values just to work efficiently. A raised to 2/3 is cube root of 8 squared, 4. Right? 1, 0, and 4, right? These are our output values. Let's write it down. 1, 0, and 4. 1, 0, and 4. Okay. Looking at this, the overall says that what should be the maximum value or the absolute
4.
maximum? 4. Excellent, right? This
Minimum
clearly.
should be 0.
Excellent. Absolute maximum, I agree, 4. And this will be absolute minimum, right? Absolute minimum. Excellent. So you see, it was very tricky. And then you go back to the choices, and then you realize that it was this one, right? Look, the critical points, remember, were -1 from the endpoint, 8 from the endpoint, and 0 that we got from the value of t that made the derivative undefined, right? And the maximum value 4, minimum value 0. Minimum value 0, right? Okay. Yeah, this is the worst this could get, guys, when the exponents are fractions. The homework, I think there is a question related to that. If you have trouble, I have attached a video there to help, but if still you don't get it, let me know, I will help. Let's see other tricky forms. I see here this one, this one. Number 4 looks very tricky. This one. What if they give you a function like this, f of r equal 1/r squared plus 2, and they ask you to figure out the maximum value, minimum value over this interval for this function? All right, let me show you how to proceed, okay? So
Quotient rule? The quotient rule?
Yeah, one choice would be the quotient rule. One choice. It's a good choice, right? But however, since I am trying to get the derivative in factor form, so that when I set it equal to 0, I can quickly pick up the critical points by solving the equation, I would recommend you do this instead of the quotient rule. Try to rewrite this way. R squared plus 2 raised to -1. These two guys are the same, right? But the advantage of this form is that I can quickly identify my outside function and my inside function, right? So I can use the chain rule instead of the quotient, right? The chain rule. So let's try to use the chain rule here. So using the chain rule, the derivative of this function should be derivative of the outside function, -1 comes up front, here -1 minus 1, here the inside function, r squared plus 2, multiplied by the derivative of the inside function. Anyone could tell me the derivative of r squared plus 2?
2r.
2r. Excellent, excellent, right? 2r, derivative of the inside function. Okay, so I got it in factor form, right? That's the advantage of using this trick. So I'm gonna get f prime of r equal negative 2r. I'm just organizing this, right? R squared plus 2 raised to negative 2. Let me bring this down so that we don't have negative exponents. So the derivative should be negative 2r all over r squared plus 2 is squared, right? Square. If you put this down, negative 2 becomes 2. Okay, great. Now, in this form, then I can go ahead and say, okay, now I am ready to set my derivative equal to 0 and then get my critical point, right? So if the derivative here equal to 0, it means that negative 2r over r squared plus 2 squared equals 0. This time is not so bad because this guy, I can get rid of this guy by multiplying top and bottom, by multiplying both sides of this equation. That's what we should say, by this amount. Look, this will eliminate this, and I will be left with minus 2r equal this guy 0, right? 0. Yeah, I have a question here on the chat. Gonja, Gonja, yeah, we are getting there. Yeah, very good, very good. Yeah, Gonja figured this out already. Yeah, and now notice, it's not a contradiction. This can be solved, all right? Sometimes contradictions, but most of the time you will get some answer. Negative 2 into 0, 0. I got a critical point, right? R equals 0. But now, this is not the only source for critical points, right? There is another, a second source that comes when you look carefully at the structure of this derivative. This structure. By looking at the structure of this derivative, anyone could tell me, oh yeah, let's close and open. Anyone could tell me, is there a way for this? What happened here? Yeah, yeah, let me just rewrite this quickly. Yeah, let me just, yeah, we said, right? So that, yeah, let's try to do this nicely so none doesn't disappear. Yeah, let's reduce the size a little bit. Yeah, very good. Okay, yeah, we said that this guy was supposed to be set equal to 0. And from there, when you multiply both sides of this by this denominator, right? R squared plus 2 squared, we ended up with this, right? This cancels this, minus 2r equals 0. And from there, divided by negative 2, we got that r equals 0, one critical point. But now, is there a way to get this undefined? Well, if you look carefully here, this is r squared plus 2, right? I'm going to write a note here. R squared is greater or equal. Someone say.
I found some numbers, but since you are mentioning something else.
Yeah, because look at this. R squared is greater or equal than 0, right? Now, if I add 2 to this expression, r squared plus 2 is greater or equal than 2. So the minimum for this expression is 2. This expression will never be 0. this is never 0. This is what is important. It's never 0, right? So when you have subtraction, yes, you can set it equal to 0, get some values of r, so that this is undefined. But here, this is telling us that this fraction will be always well-defined, because this r squared plus 2 can never be 0, right? At least worst case scenario will be 2. So we are safe. So the only critical point is this, only critical point, right? From the other source, we were not able to get critical points. So yes, r equals 0. So let's go ahead to the table. If we go to the table, then we have to, yeah, let's create a space here because we don't have space. Let's create a space here. Yeah, great. Yeah, space. Yeah, we're gonna do the table now, right? To finish it up. For the table, yes, let me use this. We have r, f of r, right? The function, and then conclusion, right? Conclusion. We start with our endpoints, which were -2 and 4, right? -2 and 4, and in between we write our critical point 0, 0, 0. We're gonna do evaluations of the original function, which is this, right? Here, original function at -2, at 0, and 4, and we'll write the answers here. Now I see that the answers are in exact form, so I'm gonna show you a trick to deal with that, okay? Yeah, recall here, f of r was originally this, right? 1 over r squared plus 2.
The
So
first one will be undefined, -2.
At -2, let's see. Let's do it manually, okay? -2 squared plus 2. -2 squared is 4. 4 plus 2, 6. Wouldn't this be just 1 over 6, right? 1 over 6 here. This 1 over 6, right? Yeah, it's not undefined because -2 squared is +4. +4 plus 2, 6, right? So we get that. Yeah, let's just continue the computation. F at 0, what would be f at 0? 1 over 0 squared plus 2. But 0 squared is 0. 0 plus 2, 2. 1/2, right? 1/2. You follow that, guys? 1/2. Very good. 1/2 here, right? The next evaluation. 1/2. I'm writing this in exact form because I saw the choices are in exact form. At 4, f at 4, what's at f at 4? 1 over 4 squared plus 2. 4 squared is 16 plus 2, 18, right? 1 over 18. So 1 over 18 here. Someone wrote something on the chat. 1 over 18. This in decimal form. It's okay, Goya, but the thing is that on the choices, they are asking us to get them in exact form, right? That's why I'm doing this.
Okay.
Yeah, but we can of course write it in decimal form, right? Yeah. So but just because of the choices are in exact form, I am doing it. Okay, great. Conclusion. Now, anyone could tell me what is the absolute maximum and what is the absolute minimum? Absolute maximum first. What do you think is the absolute?
1 by 2.
1 divided by 2. Excellent, 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 right? This one, absolute maximum, right? Think of a pizza, half of a pizza better than a slice, 1 over 6, 1 over 18,
That's literally
right?
how I see it. Yeah, that's how I compare fractions.
Yeah,
The
compare
smaller-
fractions. Think of pizzas, right? The half of a pizza, of course, better than 1/6 or 1/16. And the absolute minimum should be
1 over 18.
1 over 18, right? Yeah, very good, very good. Yeah, absolute minimum. Excellent, excellent, guys, right? Absolute maximum, absolute minimum, and these three, the endpoints together with the critical points, the three of them are critical points, right? Remember, we include them. So the answer should be going back, this guy, right? Critical points -2, 0, and 4, right? As we saw, and then the maximum value 1/2 of the pizza, right? And the minimum value 1 over 18. 1 over 18. Okay, guys. So I think with this, we should be good to go. Let me check if there's something else. Yeah, I think we did most of the exercises. And let's make this smaller. Yeah, this is similar, right? This deals with the parabola. So number 2, maybe we can do this. Yeah, no, we don't have more time, but it's set hint here. Let me write hint, set derivative equal to, this is a quadratic function, so we'll get just one critical point, and then and solve for t, right? Solve for t, for x, sorry. And then you get the value of x, and then you create your table, and then you compare on the overall what's the highest, smallest value there, right? Highest and lowest value. Yeah, this one is quadratic function, parabola, so it has just one minimum, perhaps. Parabolas, they have just one minimum or one maximum. They don't have both, right? Because they are, because of the U shape, right? So be careful there, guys. Okay, so